A very good morning to all of you. Welcome to my YouTube channel. Today I am going to teach you the Lagrange's mean value theorem. So this theorem states that if a function f is continuous in the closed interval ab, differentiable in the open interval ab, then there exists at least one real number c which belongs to this open interval ab such that f of b minus f of a divided by b minus a, this is equal to f dash c. So for proving questions, or I can say that for solving questions on Lagrange's mean value theorem, first of all we have to check the continuity in the closed interval. We have to check its differentiability in the open interval. Similarly, we have to also satisfy this condition, that is f of b minus f of a divided by b minus a, this is equal to f dash c. So if any of this condition is not satisfied, we can say that Lagrange's mean value theorem is not verified, or we can say Lagrange's mean value theorem fails there. So next is the geometrical interpretation of this theorem. So from this figure, that is figure A, it can be observed that there is no gap for the curve y is equal to f of x from the point A to B. So this shows that this curve is basically the continuous curve, or I can say the function is continuous. Also, there exists a unique tangent. This is the unique tangent for every intermediate point between A and B. So then by Lagrange's mean value theorem, what happens? There exists a point C. This is the point C in between A and B, okay, such that the tangent at the C is basically parallel to the straight line joining the points A and B. So this is basically the geometrical interpretation of Lagrange's mean value theorem. So next I am going to prove this theorem, and after proof I will also solve some examples. So for proof, what should I do? First of all, I will consider one function. So I am writing here, consider a function f of phi of x, which I have denoted by phi of x, and this is equal to basically f of x plus ax, where this a is a constant to be determined. So a is a constant to be determined such that, what happens? Determined such that phi at a, this is equal to phi at b, means the value of the function, this function, okay, this function at a, this is equal to the value of the function at b. So first of all, name above equation as equation number 1. So what I will do, I will now find the value at f of a and f of b. So I will write here phi of a is equal to f of a plus a into a, and similarly phi at b is equal to f of b plus a into b. So now these two are equal from this equation, from equation second. So I will write here f of a plus a into a, this is equal to f of b plus a into b. So from here I will find the value of a. So I will write a into a minus a into b, this is equal to f of b minus f of a, or taking a as common, so a minus b, this is equal to f of b minus f of a. So also take the negative sign, that is minus from this side. So I am going to write minus a is equal into b minus a, this is equal to f of b minus f of a. So from here the value of minus a is basically f of b minus f of a divided by b minus a. So now name this as equation number 3. So now what I will do here, I will satisfy all the conditions of Rolle's theorem in here. That is, first thing is that the function should be continuous in the in the closed interval AB. Second is it should be derivable, and third is phi of A is equal to phi of B. So I will solve these. So first of all, I will write here. Now f of x is continuous in closed interval AB. F of x is continuous in closed interval AB. So what happens? So also ax being polynomial. So this function ax is basically polynomial. So if it is polynomial, so this means it is continuous, because we know that polynomials are continuous functions. So I will write here also ax being polynomial in x is continuous in closed interval AB. So therefore this phi x, basically this phi x is the sum of two functions. So this means if ax is continuous, then other function is also continuous, and we know that the sum of two continuous function is again continuous in that closed interval. So I will write here phi x being a sum of two continuous functions, functions in the closed interval AB, continuous functions in closed interval AB. Therefore it is continuous in AB. Therefore it is continuous in closed interval AB. Okay, so I will write here now. So first condition is satisfied, that is this function is now continuous, phi of x is continuous. Now I have to show that this function phi x is also derivable. So I will write here second part, phi x being sum of two derivable functions, which one? That is f of x and a of x, in which interval? In open interval AB. So therefore phi of x is derivable in the open interval AB. Now third condition is phi of A is equal to phi of B. So I will write here also phi of A is equal to phi of B. Okay. Therefore what happens? Phi of x satisfies all the conditions of Rolle's theorem. I will write here x satisfies all the conditions of Rolle's theorem, So what happens? Then there exists at least one real number c in the open interval AB, such that f dash c is equal to 0. So I will write here then there exists at least one real number c which belongs to this open interval. I will write here AB, such that what happens? Phi dash c, it should be equal to 0. So now I will write on next page, continued. So now we know that the phi of x is equal to f of x plus ax. Now I am going to take the differentiability of this thing, or I can say I am going to derivate this function to find whether this function is derivable or not. So I will write here phi dash x. So differentiating this equation with respect to x, what I will get? I get f dash x plus a. Okay, so this implies, or I can say replacing x by c, I am left with phi dash c. This is equal to f dash c plus a. Now this phi dash c is equal to 0. Okay, so I will write phi dash c, this is equal to 0, or f dash c plus a, this is equal to 0. So from here f dash c is equal to minus a. This is the second term that I have find the value. So name it as equation number 4. So from equation third and fourth, we have what we have. We know that the equation third was basically, so I will write here, equation third was basically minus a is equal to f of b minus f of a divided by b minus a. So now I will use this term here. So I will write f of b minus f of a divided by b minus a. This is equal to f dash c. So hence the theorem is verified or proved. So this is very simple theorem. Now I am going to solve some examples on this theorem. So first example is verify Lagrange's mean value theorem for the function f of x is equal to log x in the interval close interval 1 and e. So first of all I will write here f of x is equal to this is equal to log of x, and the interval given is close interval 1 and e. Now first of all what I have to show, I have to show that this function is continuous in the close interval 1 and e. Also second thing is that I have to find the derivative of this function, that is whether this function is differentiable or not. So I will write since we know that log x is a continuous function, because we know that exponential functions, sine functions, log functions, all these are continuous functions. So I will write here first point, f of x is continuous in the closed interval, continuous in the closed interval 1 and e. Next I have to find the differentiability. So what I will do, name it as equation number first. So differentiating equation first with respect to x, what I am left with, f dash x is equal to derivative of log x is basically 1 by x. So which also exists in the open interval 1 and e. So from here two conditions are satisfied. Now as per Lagrange's mean value theorem, there exists a real number c in the open interval 1 and e such that f of b minus f of a divided by b minus a is equal to f dash c. So I will write here, since f of x satisfies all the conditions of Lagrange's mean value theorem, I am writing the short form, so don't use the short form in the paper. I am just writing here. So then there exists at least one real number c which belongs to this open interval 1 and e such that f of b minus f of a divided by b minus a, this is equal to f dash c, or I can write f at b, here b is e, so f of e minus f of 1 divided by e minus 1, this is equal to f dash c. So basically I have to find the value of c here. So now first of all I will find the value of function at e. So f of e is equal to log of e. Okay, similarly, and we know that log of e, this is equal to this is equal to 1. Similarly, f of 1 is equal to log of 1, and we know that the value is equal to 0. So also f dash c is replacing x by c in equation second. I will write this as equation second. So I will get 1 by c. So now using all these values in equation 4, I have f of e is 1 minus f of 1, that is 0, divided by b. B is e and a is 1, and this is equal to f dash c. F dash c is 1 by c. So after solving this, I will get the value of c equal to e minus 1, and we know that the value of e is basically 2.73. So this 2.73 minus 1 is equal to 1.73, and this belongs to the open interval 1 and e. So hence we will write that Lagrange's mean value theorem is verified. Next, I will solve one more example. So next example is verify f of x is equal to 4 divided by x minus 3 whole square when x is not equal to 3, and 2 when x is equal to 3 by Lagrange's mean value theorem. So first of all, what I will do here, so first of all I have to see whether this function is continuous or not in the closed interval 1 and 5. Similarly, whether this function is derivable. For continuity, when I will apply the limit when x approaches to 3, see what happens. Since I will write, since limit, when I am taking limit from x to x approaches to 3 to this function, okay, then what happens, then this term basically does not exist, because when I will apply limit to this function as x approaches to 3, then here 3 minus 3 becomes 0 and 4 divided by 0 becomes infinity. So this means that the limit does not exist. So in this case, what happens, this function is not continuous at which point, at x is equal to 3 in and which belongs to basically the open interval, which belongs to the open close interval 1 and 5. Okay, so when this now first condition here fails, the first condition of Lagrange's mean value theorem here fails, because when I put here x is x equal to 3, then 3 minus 3 becomes 0 and 4 divided by 0 goes to infinity. So this limit does not exist, means this function is not continuous at this point. So I will write Lagrange's mean value theorem is not applicable to the function f in this close interval 1 and 5. So hence this theorem, hence here this one condition, if one condition fails, then this theorem is this question is not verified by Lagrange's mean value theorem. So these are the questions and the proof of the Lagrange's mean value theorem. So now, thank you.